yesterday we started looking at Newton's 3 laws, but we only had time to look at the first 2. So Newton's first law tells us that any object in motion will remain in constant motion unless an unbalanced force acts on it. So, for example, a car which is driving along the road, that it would continue in its motion forever unless another force is acting on it. Now, we all know that a car doesn't just continue driving without us accelerating. The reason why we have to continue to accelerate is because there's another force acting on the car. So what's the other force acting on the car? So gravity is acting on the car, but that's not in the right plane. So gravity acts vertically. That doesn't oppose the force that the car's providing. There's a different force that acts in the same plane. Friction. So friction is the reason why the car will stop moving along. Gravity won't actually affect it. Now, you bring up a good point. With gravity, and this is related to Newton's third law, and we spoke about this with the table yesterday, but I'll just recap it. If gravity was the only force acting in the vertical plane pulling the car down, that would mean that the car would start going flying through to the middle of the earth, but that's not the case, because the floor also pushes back onto the car. So forces happen in pairs, and when the pairs are balanced, then the car, or whatever object you have, won't move. So we'll just have a look at this video here.
Have you ever noticed that it's harder to start pedaling your bicycle than it is to ride at a constant speed? Or wondered what causes your bicycle than it is to ride at a constant speed? Or wondered what causes your bicycle to move?
Or thought about why it goes forward instead of backwards or sideways? Perhaps not, and you wouldn't be alone. It wasn't until the 17th century that Isaac Newton described the fundamental laws of motion, and we understood the answer to these 3 questions. What Newton recognized was that things tend to keep on doing what they are already doing. So when your bicycle is stopped, it stays stopped. And when it is going, it stays going. Objects in motion tend to stay in motion, and objects at rest tend to stay at rest. That's Newton's first law. Physicists call it the law of inertia, which is a fancy way of saying that moving objects don't spontaneously speed up, slow down, or change direction. It is this inertia that you must overcome to get your bicycle moving.
Alright, so we spoke about inertia yesterday. Inertia is the tendency for things to keep doing what they're doing unless acted upon by another force. That table wants to keep resting where it is unless we have some type of force acting on it. Now, what types of objects have larger inertia? Lachlan? Yeah, or heavier objects, because we require more force to start moving those types of objects. Okay, so in a nutshell, that's what Newton's first law is. You guys are actually going to go through those modules later. We'll just have a quick look at Newton's second law, and then I'll introduce you to the third law. So, Newton's second law says that an object will accelerate in the direction of an unbalanced force acting on it. So what does that mean? If that table's sitting there and I start pushing it that way, now I'm applying more force in that direction than the opposing direction. So which way does that table want to accelerate? In that direction. Now, we also looked at the relationship between force, mass, and acceleration. So Newton's second law can be summarized using, so this is Newton's second law. We said yesterday that F is equal to ma, where F is force, m is mass, and a is acceleration. So if we know an object, if we know the force that's acting on an object and we know that object's mass, then we can work out the acceleration. Or if we know the mass and the acceleration, we can work out an object's force. So I would say that you guys would all be confident if you had different values to substitute those in. Now, if mass is measured in kilograms and acceleration is measured in meters per second squared, what are the units of force? Good. units of force are newtons. And does anyone know what letter we use? It's a bit obvious to represent newtons. A capital N. Alright, but those newtons are only measured if our mass is in kilograms and our acceleration is in meters per second squared. So just be wary of that, because sometimes you might have to do a bit of a conversion to make sure that those units are correct. So if we were to do, so here's some calculations. A zombie of mass 90 kilograms is roaming the streets when he hears a handful of survivors a few blocks away. The zombie turns and accelerates towards the survivors at a rate of 1.1 meters per second squared. So notice the units and notice that this is in kilograms. Calculate the size of the force acting on the zombie. So if we were to do this zombie example, remember, we should write down our information which is provided to us each time. So they told us what the mass of the zombie was. The mass is equal to 90 kilograms. And they told us what the acceleration of the zombie is. It's 1.1 meters per second squared. Therefore, if we wanted to work out the force acting on the zombie using Newton's second law, it would be pretty simple. F is equal to ma, which is equal to the mass, which is 90 kilograms, times the acceleration, which is 1.1, which will give us 99. And remember your units, newtons. Now, one thing that you have to be a little bit particular here with is force a vector or a scalar quantity? You guys probably, hands up for scalar, hands up for vector, hands up for I don't know. Okay, thanks for being honest. So, force is actually a vector. Because remember how a second ago I was talking about things like the gravity acting on that table, that's acting downwards, and then the force of the floor pushing back up on the table is acting up. Friction is acting one way, and the thrust of the car is acting the other way. So see how force is directional? So, but in this situation, so they said a zombie is roaming the streets, the zombie turns and accelerates towards the survivors. So the direction that you would provide in this situation is 99 newtons towards the survivors. That's your direction. All right, towards the survivors. All right, so it'd be towards the survivors. That's a little subtlety that's important. The fact that force is a vector and therefore you have to include direction. Same as when we're working with velocity, if you were to determine a velocity, you have to state the direction that the thing's moving in. But if it asked you for a speed, it didn't matter. You didn't have to give a direction. All right, we'll do one more example from here. These are all force calculations. Let's do an acceleration one. All right, Curiosity is a robot that has been exploring the planet Mars since August 2012. It has a mass of 900 kilograms and can generate a net force of 2.7 newtons. Accelerate Curiosity's acceleration. Alright, so this is Curiosity's example. Again, write down the information that they give you. So they tell us that Curiosity is 900 kilograms. And they told us the net force acting on the robot was 2.7 newtons. And they want us to work out the acceleration. Now, if we had F equals ma, Are we all comfortable in rearranging that to have acceleration all by itself? Alright, so acceleration is equal to F over M. So Lachlan, what value am I going to substitute in here?
900 kilos.
Alright, yes, but can you focus please? So no, it's not going to be 900 kilos.
Oh, on the bottom.
Yes, for the mass, our force,
99. 2.7.
alright, so just shut your laptop please. You're fine, but I can tell that Lachlan's not focusing. So, acceleration is equal to force over mass. Therefore, our force is 2.7 newtons over our mass is 900. And you can get your calculator. So, 2.7 divided by 900. Now, who would get scared if they see that on their calculator? Alright, I know that probably most people. 3e negative 0.3. Does anyone know what that means? Basically, in terms of scientific notation, you can write it as 3 times 10 to the power of negative 3. Now, who's scared by that also? Not so much. Basically, it just means that we move our decimal place back to the left 3 spots. So this is going to be 0.003. 1, 2, 3. And what are my units of acceleration if the force was newtons and my mass is kilogram? Meters per second squared. Yep.
Is our next assessment a test or
I'm going to look at doing an assignment for the next one, just because it's a little difficult to test at the moment, although we've got pretty good attendance today. Alright, so people okay with questions like that? Because in a minute when you go through the modules, you'll have to be able to do those. Alright, we will move on from, and I'm not actually going to do a mass calculation, but this would just be a matter if they give you a force and acceleration of rearranging to get mass all by itself. Alright, we'll go to Newton's third law. So, Newton's third law tells us for every action force there's an equal and opposite reaction force. For every action force there's an equal and opposite reaction force. So, if you go to hit the wall or push against this wall, so I'm pushing against that wall, why is my hand not going straight through the wall? Because the wall is providing the opposite reaction force onto my hand. Now, if my hand goes through the wall, if I push too hard and my hand goes through the wall, that means that the force that I apply to that wall is greater than the force that the wall is applying back on my hand, and therefore my hand goes flying through the wall. Please don't do that. Now, so here they've got a little animation. These two people are running towards each other, and so the force that this girl on the left applies onto the girl on the right will be equal to the force. So the two forces that they apply on each other are equal but opposite. Alright, so Newton's third law means that the force comes in pairs. When one object exerts a force on another, the second object must exert another force back on the first one. The force that the first object exerts is the action force, and the force that's exerted in response to the action force is the reaction force. Now, I just realized that I made a slight mistake in something that I just said. If I was pushing against that wall and my hand goes through, it's not that my force was larger than the force that the wall was applying. Alright? The forces are actually always equal. The forces that act on each other. The reaction force, the size of the force will always be equal to the action force. That's what Newton's third law says. Yep. So the reason why the hole in the wall happens is because you've just broken the strength of the strength of the wall wasn't enough to handle that force. But that doesn't mean that the force wasn't applying the wall wasn't applying the same force back on you. Alright. But then this comes back to the whole thing with yesterday. We're talking about if you're applying a force to a truck, alright, and I'm pushing really hard on the truck's applying a force back on me. Then I go over to a smaller object and I apply that same amount of force on that desk that I was applying on that truck, but that desk starts moving, but that truck wasn't moving. So even though the forces are the same, that table would start doing what if I applied a lot of force on it? Start moving. But the truck wouldn't if I was applying the same force. Why? Because their masses are different, and therefore Newton's second law tells us their accelerations will be different. Alright? So, like I said, just be really clear that Newton's third law tells us that those forces will always be equal. Now, these arrows that they're using to show the action and reaction forces, does anyone know what they're called? Starts with a V. They're vectors. Alright, vectors are basically demonstrated with arrows. Now, if we wanted to use a vector to represent the force acting on something, this vector shows us two things. The vector shows us the direction in which that the force would be acting, as well as the size of the force. So if I was drawing a vector diagram of, I'll just do one here. If I was to draw a vector diagram, and here's the floor, and I'm standing here. Now, if I wanted to draw the forces acting on me, I could do that using vectors. So from the center of my mass, that's where we always draw vectors from, there would be a force pulling me down, coming this way. Now, I'll measure it to make them the same length. So that's my the gravitational force is pulling me down. Now that force is pulling me down. Is there another force acting on me? Yes, because if there wasn't, I would go flying towards the floor. Therefore, the force that is also acting on me is the floor pushing back on me. Now, using vectors, I would have to draw them the same length, but the opposite direction, in the same plane. So I drew this as 15 mil, so that would mean that I would have to draw an arrow which is 15 mil going that way. And that force of the floor pushing back up, we call it the normal force. So I'll call it Fn. So see with these vectors how they're the same length but opposite direction. Therefore they balance each other, and that's when an object doesn't accelerate. When we have a balanced force, an object doesn't accelerate. But as soon as the forces become unbalanced, so if I had a car that was moving forward, the thrust of the engine's pushing the car forward. I'll do one here. Again, I know that my drawings are top class. You know what? Let's call it a train cart instead of a car. So, if there is some type of thrust causing this thing to move forwards, remember you always draw the vector from the center of the mass. There's some thrust pulling this forward, Ft. Now the only opposing force in the same plane, in that horizontal plane, is what? Friction. Now, if I was to depict friction using a vector, the arrow is pointing in the other direction, but the vector would be smaller, because the length of the vector demonstrates the size or the magnitude of the force acting. So it's in the same plane, going this way. We've got F friction. Therefore, since this vector is greater than this vector, we have unbalanced forces. The cart will go that way. If the thrust force was balanced by the frictional force, then the thing won't move. You know how initially you're trying to push something to get it moving, and it's a bit difficult to get it moving? That's because the force that you're applying is initially balanced by that frictional force, and then eventually you can overcome it, and then it starts moving. So, is there any questions? Did you have a question? Okay. Just take note though, there would also be gravity and the normal force acting on it, but I'm only considering the forces in that plane here. Yeah? So, they look at if you were an astronaut in space. This is a good little example. If I was an astronaut in space, which was my childhood dream, unfortunately that didn't come to fruition. If I was in space, Earth, if I was moving like a satellite, I'd be going around the Earth because there's a gravitational force pulling me towards the Earth. I wouldn't just go flying off into the abyss. But would I be applying a force back on the Earth? Am I applying a gravitational force on the Earth? Yes. All objects have a gravitational attractive force to each other. So me and that desk there, we're attracted to each other. But why don't they start moving? Because the force of attraction is very small compared to our mass. Therefore, the desk doesn't come flying towards me. In the situation of me going around the Earth's mass is really large, my mass is really small. So I can feel the gravitational pull of the Earth pulling me around the Earth, but the Earth wouldn't move because it kind of moves, but because its mass is so large, we wouldn't notice that movement of my force pulling it towards me. Alright. We'll leave that there. So there's 3 modules. There's Newton's first law, second law, third law. The first and third are quite short. The second one might take a little longer. The second one has some of those mathematical type questions, calculations like this, so you might need some paper to help you do those ones. Alright?